This section on general performance principles deals with the factors that control and determine the performance of an aeroplane throughout the different phases of its flight. We will start with the takeoff and then proceed to the climb, descent, en route, and lastly the landing phase. This first lesson deals with the takeoff. The takeoff stage of flight is defined as being from brake release until the aircraft reaches a specified height, called a screen height. The screen height varies from 50 feet for Class B aeroplanes to 35 feet for Class A aeroplanes. As the aircraft accelerates down the runway, a speed will be reached where the pilot applies back pressure on the control column to raise the nose wheel off the ground. This procedure is called rotation, and it is initiated at an indicated airspeed which is called VR. From rotation, the aeroplane pitch attitude will increase, and eventually the main wheels will lift off the runway. The speed at which they do so is called VLOF. After this point, the aeroplane starts its initial climb, and eventually will reach the screen height. However, a specific speed needs to be gained before the screen height. This speed is called the takeoff safety speed. There is a certain minimum value associated with this speed, which is usually based upon the aeroplane's stall speed and/or its control speed, but these will be dealt with later. In large twin-engine aircraft, the takeoff safety speed is commonly referred to as V2. The takeoff can be divided into two parts. We call these the ground run and the airborne section. The first part, the ground run, is usually referred to as the takeoff roll required, or the takeoff run required, which is the distance traveled from brake release to liftoff. The second part of the takeoff, the airborne section, is commonly referred to as the initial climb. This is the distance covered from liftoff until the aeroplane reaches the screen height. The combined length of the takeoff run required and the initial climb is known as the takeoff distance required. As pilots, we need to make sure that the takeoff distance required does not exceed the available distance at the aerodrome we are using. This can be achieved by checking those factors which affect the takeoff distance and ensuring that the performance achieved will still enable us to take off safely within the constraints of the airfield. This may seem obvious, but there are many incidents to suggest that this important consideration is often forgotten. A long takeoff distance is considered to be poor performance, whereas a short takeoff is considered to be good performance. However, in commercial transport, the performance is not measured in terms of the takeoff distance, but rather in terms of the weight that can be carried. A good performance, in terms of a commercial flight, would be a takeoff with a large weight, whereas a poor-performing aeroplane would only take off with a small weight. As a general rule, any effect that would cause the aeroplane performance to reduce would cause the aeroplane's takeoff distance to increase and/or to reduce the takeoff weight. To better understand takeoff performance, we need to fully grasp the forces acting upon an aeroplane and how these forces might change throughout the takeoff. Shown on screen is an aeroplane at rest at the brake release point. A typical 737-400 series has a maximum all-up mass of 68,000 kilograms. This mass will be accelerated from the center of gravity of the aeroplane towards the center of the Earth by gravity. The resulting downward force is called weight. The objective of the takeoff procedure is to create a sufficiently high enough force to oppose this weight and allow the aeroplane to fly. The principal force which is used to oppose weight is lift. In simple terms, to generate a lift force, we need a mass of air to pass over an aerofoil. The aerofoil in our case is the aeroplane wing. To make the air flow over the wings, the aeroplane must be pushed through the air. The faster the aeroplane travels through the air, the more lift will be created. The aim at takeoff is to gain a sufficient amount of forward speed to create enough lift to help counteract the weight, and thus allow the aeroplane to fly. However, in order to move the aeroplane through the air, there must be a horizontal forward-acting force. This forward-acting force is generated by the engines and is called thrust. With a given amount of thrust, the aeroplane will accelerate and air will flow over the wing, thereby creating lift. A detailed explanation on how propeller and jet engines produce thrust is beyond the scope of this course, but nonetheless, brief explanations will be provided at appropriate times. The basic concept of the modern jet engine is that it draws a large mass of air through its intake and accelerates it, and finally ejects it. The principle involved here is mass multiplied by acceleration produces a force. This is an adaptation of Newton's second law of motion. The greater the acceleration of air, or the greater the mass of air, the greater the thrust force produced. However, as the aeroplane travels faster, the velocity of the air entering the engine starts to match the velocity of air exiting the engine. The result of this is that the air is not being accelerated as much, and thus less thrust is produced. So, as the aeroplane speed increases, the thrust produced by the jet engine decreases. This loss of thrust with increasing forward speed is referred to as intake momentum drag. When the aeroplane reaches speeds in excess of 0.2 Mach, then the air ahead of the engine starts to compress, increasing the air density, and therefore increasing the total mass of air flowing through the engine. As a result, this helps to limit the loss of thrust caused by intake momentum drag. This thrust recovery is called ram recovery or ram effect. So initially, as speed increases, thrust will fall, but above 0.3 Mach, the thrust loss starts to reduce due to the ram effect. In the speed range used for takeoff, the jet engine aeroplane never attains sufficient speed to gain the full ram effect. Therefore, in takeoff, as the jet aeroplane accelerates down the runway, thrust will reduce. The propeller engine generates its thrust in a similar way to the jet engine. A mass of air is still accelerated rearwards, but the propeller is acting much like a wing, in that it produces lift, only this time in a forward direction. You will recall that if a mass of air were to pass over an aerofoil, then lift will be produced. In order to pass air over the propeller so it can generate lift, it must be turned through the air by the engine. Shown here is a propeller in cross-section. The amount of lift produced by the propeller blade and the amount of air that is displaced backwards is a function of the angle of attack. The angle of attack is the angle between the relative airflow and the chord line of the aerofoil. The greater the angle of attack, the greater the lift force, and the greater the amount of air displaced rearwards. When the aircraft is stationary, the airflow relative to the propeller is from beneath, as shown. However, as the aeroplane gains forward speed, more of the airflow comes from the front, and as a result, the angle of attack and subsequent lift produced will decrease. So, similarly with the jet aeroplane, a propeller-driven aeroplane will experience decreasing thrust during the takeoff. There is one more force to consider. As the aeroplane accelerates down the runway, it will encounter several forms of resistance, called drag. Resistance from the air is called aerodynamic drag, and resistance from the wheels and the runway is called wheel drag. We'll deal with aerodynamic drag first. Aerodynamic drag has two forms, parasite drag and induced drag. During the takeoff, the only form of aerodynamic drag to concern us is parasite drag. Parasite drag is created by the impact of the aeroplane on the air. It follows then that as the aeroplane travels faster through the air, parasite drag, and thus the aerodynamic drag, increases. Therefore, during the takeoff, aerodynamic drag is increasing, as shown in this graph. Having discussed aerodynamic drag, let's now consider wheel drag. Wheel drag is basically the friction between the wheel and the runway, and is a function of their frictional coefficient and the load placed on the wheel. As an example of this, press your finger lightly on the desk and push your finger forwards. You will notice a resistance to the motion of your finger. Repeat this scenario, but now press down harder. You will notice much greater resistance to the motion of your finger. This example aptly demonstrates that the greater the load placed on the wheels, the greater the wheel drag. Returning to the takeoff, as more lift is generated by the aeroplane accelerating down the runway, there will be less load on the wheels, and thus the wheel drag will decrease. Wheel drag will eventually reduce to zero once the aeroplane has achieved liftoff. To summarize, aerodynamic drag increases during the takeoff, whereas the wheel drag decreases during the takeoff. As illustrated on screen, the total effect of the drag on the aeroplane is that it increases with speed up to liftoff. Adding the thrust line onto the graph, you will recall that for either the prop or the jet aeroplane, it was stated that the thrust decreased during the takeoff. At the start of the takeoff, you can see that there is a large margin of thrust in excess of the total drag. This is shown by the blue area between the drag and the thrust lines. This excess thrust is what is used to accelerate the aeroplane. Notice, though, that as the aeroplane gains speed during the takeoff, there is less and less excess thrust available, and therefore less acceleration. Next, we'll examine what determines the takeoff distance, and also what roles the four forces play in determining the takeoff distance. In order to do this, let's briefly examine the formula that is used to calculate the takeoff distance. The letter S is the displacement or distance required from rest to reach a specified speed, which is v, with a given acceleration, a. Acceleration is force divided by mass. The force is thrust, minus aerodynamic drag, and minus the wheel drag. Expanding the formula in this manner allows you to see how a change in one of the variables has a knock-on effect on the takeoff distance. For example, if there is a reduction in thrust, acceleration will reduce. If acceleration reduces, then the distance required to a specified speed increases. Although we have already mentioned how some of these variables change during the takeoff, we'll now analyze in detail all the forces that can affect the takeoff, with our principal concern being how these factors affect the takeoff distance.